we're jumping into acids and bases, and we're not going to wait long, we're just going to hop in. So we might just do Roman numeral 1, and we're going to do some definitions. Some of these you have seen before. The main one that's going to be new is Lewis acids and bases, but some of it's going to be a repeat. The other thing, just acid plus base always yields salt and water. I think that's been driven into your heads by now. Acids taste soury, bases are bitter, and with that we'll hop into definitions. So the first definition, just kind of based on time, was the Arrhenius definition. Sometimes it's pronounced Arrhenius, Arrhenius, either way. And this one is kind of the most traditional, and it says that acids, or it defines acids as anything that dissociates in water to make or produce hydrogen ions. And again, that's the most basic definition. In general chemistry, that's what you would have learned. I'm not exactly sure what you get in college chemistry, but acids dissociate to make hydrogen ion. And our probably easiest example of this would be hydrochloric acid. When we put it in water, we get H plus and Cl minus, so we call that an acid. All right. And then kind of the other thing to know about that is H plus, or you might put hydronium, and again we covered this first semester, which is really H3O plus. Alright, so H pluses don't really exist. Often we write them just for shorthand. And then bases are simply defined as dissociate in water. So we're just going to repeat this. So carrots dissociate in water to make hydroxide. And that is a base. Alright, an example for base, on this traditional example would be sodium hydroxide. If we put it in water, we get sodium ions and we get hydroxide ions. So if we have hydrogen ions floating around, we have an acid. If we have hydroxide ions floating around, we have a base. And then again, you might just put acid plus base, always yields salt and water. This works well most of the time. Alright? But Bronsted-Lowry is kind of the more typical. This is usually the definition that chemists are going to use. Bronsted-Lowry, it's two guys. I believe it's two guys, and I think it's just R-Y. But Bronsted-Lowry definitions. Alright? And they change it up a little bit. We're going to see the examples are basically the same. But with the Bronsted-Lowry acid, we're going to define it as a proton donor. And again, I believe we had this first semester, but what is a proton? A proton is simply a hydrogen atom. So a proton donor is an acid. And a base is a proton acceptor. So something that can accept a hydrogen. Nope, I don't want to put acceptor there. I want to put proton first. So a proton, or a hydrogen acceptor. Alright, and then kind of the new thing that we're going to introduce is in these reactions. This popped up a couple times on our equation writing from a couple units ago. Alright, but anytime we mix an acid and a base, it is true that we get a salt and water, but with these definitions we also might say that we get a conjugate acid. Conjugate acid plus a conjugate base. I'm just going to abbreviate it this time. But if we mix an acid and base, we get a conjugate acid and a conjugate base. Alright? And what that looks like is, our example, we're going to put hydrochloric acid, and we're going to mix it with water, and we're going to get hydronium, and we're going to get chloride ions. Okay? And we're just going to define this as, this over here, who is donating the proton? It's going to be hydrochloric acid, so this is our acid on the left-hand side, and water is acting as our base. Okay? And then really, what is paired with hydrochloric acid? It is donating the H. So the chloride ion is the conjugate base, all right? Because it's kind of paired with our hydrogen. It's one hydrogen different than our hydrogen chloride or hydrochloric acid. And then water to hydronium, it is one hydrogen different. So hydronium is our conjugate acid, all right? And conjugate just means pair. So we have one pair, which is hydrochloric acid and chloride, and we have another acid-base pair, which is water and hydronium. All right. Our other example is going to be ammonia plus water. All right. And in this example, we're going to get ammonium. Whoops. We're not going to get anything. We're going to get ammonium, and we're going to get hydroxide. All right. So again, over here, who is donating? Well, our water is now donating. So water is acting as an acid. And notice up here was acting as a base. So it can act as either an acid or a base. And our ammonia is acting as a base. And over here, our pair with ammonia is going to be ammonium. So it is the conjugate acid. And then hydroxide is our conjugate base. All right. And again, these are pairs. The only thing that separates them is a hydrogen. So it's pretty easy to see which one is which. And again, it's kind of nice to see that water can act as either. And just a term that you should be familiar with is water is amphoteric. So ampho meaning both, like amphibian, both live in land and water, and it's amphoteric. And I don't have any idea what the teric means, but that is just our phrase for being both an acid and a base. Our next letter is we're going to talk about acid strength. So strength of acids. How can we determine which acid is stronger than another one? And all the strengths are, it's affected by polarity of HA bond, all right? Where A is just some random acid, okay? So hydrochloric acid, A is Cl. If it's sulfuric acid, A is a sulfate ion. But just that bond between H and A, which is the rest of our acid, whatever that acid happens to be, all right? So a couple of rules apply. If we have a binary acid, so B-I-N-A-R-Y, binaries, it is simply H with some anion, A minus. Okay, so binary just means two elements, so HCl, H2S, but we have H with one other thing. If this is true, we have a couple trends. We have a group trend and a period trend. And obviously groups are columns, periods are going to be rows. So our group trend always has to do with size, right? And as we go from top to bottom, what happens to the size of atoms? They get larger. What happens to the size of ions? Because again, we're talking about anions here. They get larger as well. So we might just say the larger the anion equates to a weaker bond, all right? Because our proton's a little bit further from our electrons, they're not as strongly attracted. So larger anions have weaker bonds. And if we have weaker bonds, it means they're actually easier to break apart. So we have stronger acids. All right, because strong acids completely dissociate. So we want our bond to be weak so it can break apart. So if we compare HCl to HF, all right, so F is in our second period, but within a group, it's in our 17th group, but within a period we have F, which is above Cl. So which one of these is larger? Cl is larger. So because it's a larger anion, it's a weaker bond, it's a stronger acid. All right, which again, who's going to be stronger, HCl or HBr? Because we know hydrobromic is another strong acid. It's stronger than hydrochloric. And then we can also say that hydroiodic is even stronger than hydrobromic. And then why is HF not considered a strong acid? It doesn't want to dissociate because fluorine is so electronegative, it holds on to its H so strongly it doesn't break apart. Okay? So we can have group trends, we can also have period trends. So across a column or across a row. And periods basically boil down to polarity, all right, and electronegativity. So as a group trend, or as a period trend, as we go across a period, electronegativity increases. Who's the most electronegative? Fluorine. So we might just say from left to right, electronegativity increases, which means more polar. And if it's more polar, we have a stronger acid. Stronger. So we might compare, we'll do HCl and H2S. Alright? So stuff to the right is going to be more strong than stuff to the left because it's more electronegative. So again, hydrochloric is stronger than hydrosulfuric. Okay? And that takes care of binary. So binary is just simply H with one other element. The next thing we're going to look at is ternary acids. So things with more than one element, or something other than just hydrogen plus two other things. And these always fall in the category of oxo acids. So they're acids with oxygen in them. So nitric acid, sulfuric acid, nitrous acid. But they always have oxygen. So we're just going to write this as kind of in this format, where we have H, and we're going to have some M number of H's. And then Y is going to be some nonmetal, so sulfur, nitrogen, chlorine. And we're going to have O, and then our number of O's is just going to be defined by N. We might say where Y is a non-metal. Alright? So a couple things. If we have the same number of H and O, alright, so M and M are identical. What is true is the higher the electronegativity, of Y, okay, because that's our nonmetal, the higher electronegativity, the stronger the acid. Stronger acid. So an example might be H2CO3 compared to H2SO3. Okay, so both of these have the same number of hydrogens, 2 hydrogens and 3 oxygens. But if we look at the periodic table, who is closer to fluorine? Sulfur is. So sulfurous acid is stronger than carbonic acid. Okay. The other thing we can look at is the same Y. So the same nonmetal, same Y, but different numbers of O's. Different numbers of oxygens, or N is changing. Alright? And this one is simply more O's equals stronger acid. And again, there's several examples that kind of fit here. If we have H2SO4 compared to H2SO3, which we kind of had above, you know that sulfuric acid is a strong acid. Well, sulfurous is not. And it's simply that other O pulls more electrons from S, which makes it easier for H to be released. Okay? And then lastly, you need to have these memorized. We've gone over these before, but know that HCl, HBr, HI, H2SO4, HNO3, and a good one to add is going to be HClO4, perchloric acid. Those are 6 strong acids. If it's not one of those 6, it's going to be a weak acid. Alright? The very last thing we're going to cover is just some equations for calculating pH and acid concentration. So I'm just going to leave this measurements, maybe calculations, but how do we actually measure pH or concentrations of acids? Okay, because that has to do with strengths. So measurement, let's just do brackets, acid concentration and base concentration. Alright, we do not need to have a whole lot of acid for something to be considered acidic. So the concentrations are really, really, really small. And because they're small, we use a logarithmic scale, alright, which is just an exponential scale. So we might say A, and just define this as pH scale, right? This is a scale you're familiar with. It just is a running line of, let's say, 0 to 14. 7 in the middle is considered neutral. If it's less than 7, it is an acid, and if it's greater than 7, it is a base. All right. And then we're gonna have some equations. Equations. All right. And here are the equations you kind of need to know. I believe they're on your equation sheet. I'm just going to list them, and as long as you can use a calculator, these equations shouldn't give you any kind of problem. But here they are. Our first equation is pH equals negative log of hydronium or hydrogen concentration. So if we know the hydrogen concentration, if we take the log of that, it's going to be a negative number because our concentrations are so small. They're going to be 4 times 10 to the negative 7th, 4 times 10 to the negative 2nd. They're going to be really small numbers, so our log of that is going to be a negative value. And if we take the negative of a negative, we get a positive value, because pH should always be positive. The inverse of that, if we want to know the concentration of hydrogen or hydronium, it is simply 10 raised to the negative pH. Alright? And obviously the log is going to be base 10 if that's the case. The next thing is we can calculate pOH. Alright? And pOH is going to be the same kind of idea, such that we're going to take the negative log of hydroxide concentration, and then conversely, OH concentration is going to equal 10 raised to the negative pOH. Alright? And then these next two equations are helpful. pH plus pOH always equals 14. Alright? And then our other equation, which is kind of the idea of this, using all these equations kind of combined together, hydrogen concentration times hydroxide concentration will always equal 1 times 10 to the negative 14th. Okay? So real quick, if these are identical to each other, if hydrogens equal hydroxides, alright? So we might say, if we know hydrogen is x, then hydroxide is also x. So we would set x squared equal to 1 times 10 to the negative 14th. Alright, so we're going to take the square root of both sides. We're going to find that x equals 1 times 10 to the negative 7th. So if this is our concentration, alright, and we take the negative log of that, our pH equals 7. So again, that is why at pH 7, it's neither acidic nor basic, because it has just as much hydrogen ions as it does hydroxide ions. Alright? One thing to kind of point out, anytime you have an acid, there's always some amount of base in the acid. Alright? The stronger the acid, the less hydroxide you have. The stronger the base, the less hydrogen ions you have. And when it gets to 7, you basically have equal numbers. And the closer you get to 7, the closer those are to being equal to each other.